So thank you for coming, and we are going to start with this session. Our speaker is Luis Acosta. He's going to talk about approaching interesting nuclear processes from the developing of new instrumentation. Thank you very much, Luis.
Thanks, Daniel, and thank you very much to the organizers for this invitation. Well, I'm in my country. I'm very happy to be here, as usual. But I'm happy to be here as well because this is I studied physics in this faculty many years ago now. And what's curious, I've never been in this platform before. So it's something strange. Let me just mention that this auditorium was used for many years to project some movies, very nice movies, more very, in the case of classical cinema, and there was very funny years every week to have a film here, and every year a marathon film all the night, and just to remember. Well, I'm here to speak about some of the instrumentation that was developing here during the last 10 years, and what things that we are developing now there in Madrid, where I'm presently. So let me start with some first introduction. Let me put it here. Well, first, during the last 20 years, the nuclear physics, as you know, was benefit with impulse of new technology for the developing, particularly of larger facilities to make some new nuclear studies, in general, to make some kind of new species, to produce better currents of beams and most energies. So many of these performers are still running. So some of them are practically finished, but we are on this run. So in parallel, several collaborations have developed a number of new devices to take advantage of all these future beams, all these future facilities, and some upgrades of the presently arrays available. Those detection arrays, different kinds of targets, separators, scintillators, big arrays are created or under construction. So in this presentation, I will visit some of these devices that we start to prepare some years ago, and a very recent that we start to make, led by a Spanish institution, but also involving Mexico. So particularly, I'm going to speak about one silicon array detector that we developed during the last more or less 7 or 8 years. That was successfully proved in 2019 in some measures at Twin Sol and Tri-Sol facility in Notre Dame University. And then the second element that we're going to mention is the supersonic gas jet target that we have here in Mexico, that is sugar. And which is part of a new collaboration that we call Sugar at LNL. And the idea is collaborate with the Laboratorio Nazionale di Legnaro from the INFN in Italy. Finally, I present the very, very recent project that started just the last year, which is called ISRS Magnum, which will be some kind of future spectrometer, isotope separator, which is under demonstrator phase, and which is expected to be installed as part of the beam line that is called SEC at the High Solder facility, probably at the end of this decade. So I'm going to start with this CMAS array, that is an array of silicon detectors for nuclear studies that, just first mention that we have, I have the opportunity in the past to participate and practically make all the idea and construction of these two arrays. The first one is Gloria. That is this very nice array of silicon detectors that is more or less in 3 dimensions. It's some kind of balloon where all the detectors are tangent to one imaginary sphere. It was working in many experiments since 2010 in different labs as Ganil, ISOD, and so on, and also in the lab of Huelva. And it's continued being using, and now it has a second version as far as I understood. And then during my first or second postdoc, I think, I was working in Catania, developing this array that is very nice, it's Barcos. This design was made by one of my students here in Mexico, that is called Cesar. And then, well, we start to make the first prototypes going through this kind of design for the particle correlation. This is Farcos. This is more complex than Gloria. It has cesium iodide, two silicon detectors. And more or less with all this knowledge, I start to build a new array here in Mexico. Well, this is called CIMAS, which the meaning is Sistema Móvil de Alta Segmentación, high segmentation mobile system, that was thought to be used, first of all, at LEMA, which is our most modern lab here in Mexico. Much modern accelerator, we can say, is most of the uses for AMS, but also it has a beamline. So we need some kind of detector system. So we start with the things that we know very well, that was these square telescopes that we use many times. So we thought in 4 double-sided silicon strip detectors. At the beginning, we have just 2 because we have, of course, in Mexico, there are not big grants to start something and finish. You need to go step by step. We start with these 2 guys formed by 2 like this. The good advantage of silicon detectors is that we're very thin, 20 micron. I don't know, there is a 20 micron. And a double-sided silicon strip detector. And probably there were the first detectors that were produced by Micron in these conditions of double-side. Then the idea was also to include some telescopes to make some astrophysics, which are more simple. Surface barrier detectors of 15 microns, and followed by E-detectors, PIPS detectors of 300 microns. And well, 1 square centimeter of bacteria. All the project to make in a 3D printer to hold this detector was held by these 2 students, Fausto Morales and Carlos Flores. And in parallel, we have the opportunity with also with these grants related to LEMA to purchase this data acquisition system, which is FEVEX. Maybe some of you know it. It was made at GSI, and we have here in Mexico Tunic Kurz that was the responsible of this creation of this kind of cards. Are ADCs of 16 channels, which is practically 60 megahertz, 12-bit, and an input from 1 to -1 volt, and a sample of sample rate maximum as 65 megasamples per second. So it has 2 different models, so the Spexor and Trixor, which are directly in a FPGA circuit, which is working as trigger. And we start this test with 64 digitalization channels, and presently we have 128. We use a silicon strip detector, these first 64 channels, and we make the characterization of this to start to work here. And at the same time, later on, we purchase also some channels for timing digitizing. This is the results of this test. The trace that was produced for one of the strip of this detector, and the alpha spectra that is spectrum that is very nice. So with a very good resolution, and this is finally just the same alpha source, but in combining 2 strips from this kind of detectors. In the case of small ones, well, it was part of the thesis of the master thesis of Luis Enrique Charon, which is presently doing his first postdoc at Triumf. So we measured this reaction, just a try, the first time in LEMA, and we have some events, not totally sure that were alphas coming from these reactions, but the experiment was good because we could try all the system with the 4 telescopes, and we got very, very nice results in the case of the resolution of these 4 telescopes. Now are continuing being using in some experiments performed by Daniel Marin here at LEMA. This is the commissioning of the thin detectors of sugar. This is more or less, I put this photograph because it's very important how you can control very well with a 3D printer, how you can, the kind of pieces that you need to perform. We put this lock in the cable because this detector, as my Brazilian friends can remember, are very, very, very thin. So it's very easy to break. And we use this lock to lock the cable, and we isolate completely the detector from the other elements. And with this, we have very well protected the detector to use in different chambers. So this is a strip. The resolution is not the best, but this is usual in this kind of detector. But the advantage is that we have pixelation, so we can get at the end a very good resolution. Well, CMAS was a very good pretext to start to collaborate again with Notre Dame Laboratory. The ININ, the Instituto Nacional de Investigaciones Nucleares, which is close to here, 30 kilometers from here, it has, for many years, they collaborate in the last 2 or 3 decades with the group of Notre Dame and also with some groups from Brazil, the University of Sao Paulo. So with this array, we say we are ready to restart something or to try something in this condition. So we went there. Well, first of all, we make a proposal. We contact some friends. But let me just show you my first experiment. I'm here. I'm younger, 2010. Here is Eli Aguilera, is also younger too. So here is, you can, maybe some of you can recognize this guy, which is Jim Colata, with the big panel of the CN accelerator there at Notre Dame, where they have twin sol. And this is one very nice article that was probably the first one of the dynamics of boron 8 that was produced at Notre Dame and with many authors. I'm here, but obviously that was led by Eli Aguilera. So in the present years, we start to make again this collaboration using now CMAS, an array coming from Mexico, to start to make again experiments. So I have good colleagues in many countries. One of the persons that I work a lot is Athena Pacu, which is a professor, an emeritus professor from University of Ioannina. And she proposed to measure again weakly bound nuclei there at Notre Dame. And well, we start to make some kind of proposal, involving also Angel Sanchez, which is from Huelva, and some people from Catania, in this case is Basilis Uqueras. And we made the first proposal to Jim Colata, and Jim Colata, start to work with him, which is Patrick O'Malley. He's in somewhere here, maybe, I don't know where. Well, we can search. It's here. It's Patrick. So then in 2022, we turned back to Notre Dame to make a new experiment. And finally, in 2023, we make the last one. This year, we have another kind of event I'm going to speak about later. Just to say that this collaboration start to run again, and that we are doing good measurements using CMAS, and in this nice laboratory. So this is how looks our setup there. When you have the 3D printer, you can make very fast a piece and fix your angles. So we can make many of these kind of pieces with the very well measuring angles fixed. So then you have to send this. Well, we put in the suitcase and we take the flight. We go to Notre Dame, and then we reassemble everything there. Here is on the chamber. This is the chamber that we use that is connected directly to twin sol, which is behind of this wall. And how is the piece adapted to the chamber of Notre Dame? This is the name of the proposal that was promoted by Athena, Jim Colata, and me for this August in 2019. It's the kind of the spectra, as you can see, is extremely dirty. We have a primary beam, but this is the boron 8 that we are searching. So with this time filter, we can work and apply the coincidence between this time filter and the delta E spectrum. So we can clean very well the spectrum, and these events that remains there, we are sure that are related to the elastic or breakup scattering. So this is the breakup that we measure, this direct breakup that we measure in this experiment, that was finally published in this PRC in 2020. We finished very happy. So happy to make a new experiment that was in 2022. In this case, with important modifications. Now the proposal was middle mass zirconium, as well with boron 8, but also with beryllium 7. The changes were principally that we have two more telescopes, one of these coming from Huelva. The advantage of this species is also that you can put many other detectors, and if these detectors are more or less in the same conditions, you can adapt to this to your system. So we have 4 telescopes here. And in the case of twin sol, it was probably one of the first experiments of trisol, which is the third solenoid that was mounted before of the wall. Our chamber were sited here. I took this photo on the internet. I never took a photo of the complete array. I don't know why. So, and it was the previous array. So the new spectra is very clean, as you can see. And well, this is the advantage coming from the trisol solenoid. These are the new results. We measure beryllium 7 on this natural zirconium and the quasi-elastic scattering for many energies. As you can see here, well, there is a fuel CDCC and not including the continuum, and apparently this kind of nuclei is practically not depending of the continuum states of the continuum discretized. So these results were published in this PRC in 2023. And later on, the elastic scattering of boron A was also measured and, well, finding more or less the same, more similar to one optical model potential than the use of CDCC. So this article was published 2 days ago. Two days ago, yes, 2 or 3, I don't know, also in PRC. So it was a good consolidation of these measurements in Notre Dame. Finally, let me speak about this experiment that was not related with CMAS. We use an array coming from what that was mounted there in Notre Dame to measure again the helium-6. The idea is to measure the small angles of helium-6 that are not reported in the literature, and they have some important compromise in astrophysical measurements. So this is the helium-6 that they could produce, and well, we are under analysis. We made just this experiment just the last year. We have a very preliminary results I'm showing here. So this is the separation of the primary beams and secondary beams. And well, the last week, just for mention, this experiment was supported in the most part by IRENA, which is the present network of astrophysics. It's from Mexico and Brazil, Spain, and Portugal and Argentina. And it's associated, IANA, sorry, is associated to IRENA, which is the American one. And we have the first meeting last week there at Notre Dame. You can see here, it's out of the hotel. This is a photograph. But this is all the people considering students, postdocs, and some of, and many researchers, and was a very good one. Well, I finished this part of the talk related to this silicon array. CMAS to start to speak about the gas jet target that we have here also in Mexico, that we call Sugar. It's a very nice, I love this name. So Sugar, this is the meaning. It's a bit forced, but it's there. Supersonic gas jet target, and it's this array, the system, this is the design. And it has the capability to produce a gas target at supersonic velocities, and the gas is continuously going in and going out with this robust pumping system. And this part, which is the differential vacuum system, allow the known conditions to maintain the reaction chamber in a windowless mode. It means that there is a free way from the beam to pass from here, which has to be connected the beam line till the end, where is the target. So this is the good characteristics of Sugar. And they are the components that are very well identified, the part of the differential vacuum system, the part of the jet pumping system, and the reaction chamber or jet chamber. So how it works? Well, we have this train. This is curious because the students start to call train because all these chambers were attached ones to each other. So we start to make the differential vacuum here. We start with one turbo and then with 2 diffusion pumps that are very powerful, as you can see here. And then they have a very small interconnections with KF for nipples and the collimators around 5 millimeters mounted inside. This is the part of the differential vacuum system. Then the next step is to connect to the jet chamber, which is bigger, where we have inside, well, connected to this pipe, gas bottle, and the jet is producing here, and the gas is being extracted from here, and we have some valves to launch every system one by one. Finally, the jet is producing by this high-speed mechanical pump, which is a HENA 200, which is here, and the spilling gas around of the chamber is getting out with this strong system, which is first a high-speed root pump, and to 1 second root pump, and finally a mechanical pump also here. This is the complete part of the jet, and we have these pieces that first is the nozzle, which is where the gas is entering. There is a very, very small aperture, and the catcher, which is the spy that is inside and is connected directly to this HENA pump. This is just a picture of some cartoon of how looks the jet inside, or how we thought that it looks. This is the beam, this is the jet, which is gas in circulation, and these are the differential of the different pressures. We start with 1.15 Thor, which is the nominal value that we have every time that we produce the jet, and then we have different vacuums coming from the differential vacuum system till arrive till 1.6 times 10 to minus 6, which is the chamber that we can connect directly to the accelerator. This is the commissioning that we developed of this system, which was in 2015. And this is the jet. Here's Efraín Chávez, which is one of the guilty of the construction of this system, but the main guilty thing is Francisco Favela. He was a student that developed everything to produce this for his PhD thesis. We make this test using a delta E telescope with a beam of deuterium produced by the Van de Graaff accelerator. You can see here the big magnet of the bending magnet. And this telescope, 60 micrometers plus 11 micrometers, very thin one, and theta lab of 35 degrees to study the reaction, deuterium alpha, with nitrogen coming from just air that we practically open the bulb and we have a big, nice target of air. The target thickness that we found was 10 to 18 atoms per square centimeter, and the energy projection very well of 200 keV. As you can see in these alphas, that is the good image of presentation of this system, that we can separate very well the alphas producing by this reaction, and we published this work in the same year in 2015. So, motivated by one of my colleagues and friends, Javier Valiente Dobón, when he was in Mexico some years ago, well, he was impressed about this system, which is more or less simple. And he proposed me and my colleagues here in Mexico to make some kind of proposal for the arriving to Leñaro, this big array, that is the gamma tracking array, Agatha, which is a part of European collaboration, and also NEDA around 2020. So they make this meeting to receive some letter of intents for new experiments there. And we propose this, some physics cases to present in the possibility to use sugar along to Agatha and NEDA and a charged particle, making a unique opportunity to measure charged particle gamma and neutrons simultaneously with the use of a very thin pure target. So we sent to Daniel Marin to Leñaro, and he defended this proposal. It was very well accepted, and now is part of the program inside of Leñaro as the program for 0 degrees experiments. This is our workhorse reaction. It's the first that we proposed. We proposed 3 more, and it was well related with this is a famous reaction, oxygen, which is related with oxygen burning. So it's this reaction will finish in this sulfur 32, also in silicon 28, 90% of the time. So they are production of many other guys. And during this process, we can open this channel. So we have neutrons, protons, deuterons, and alpha that we can detect. But also in these steps inside of, well, covering the reaction, we have also some gammas in the different stages. So it's a perfect opportunity to try all these detectors at the same time and simultaneously. Moreover, we have the numbers related with this reaction. So we can see here that there are the big discrepancy, the predictions. There are no data in this region, and this is one of the interesting regions for T9, which is 4 to 14 MeV. In the case of T9 is 1 to 4 in the case of astrophysics interest. So the idea is to cover from 4 to 13, more or less, using the tandem with 2.7 to 4.9 MeVs in the high voltage platform, using 2+ charge state, and the high intensity available. And obviously the low cross section is intended to be covered for the triple identification of gamma and neutron particles. So we start with this proposal. We have 3 proposals more to use with sugar, and we are totally open to continue working with new collaborations, because it will be part of these facilities to be available for 0 degrees experiments with Agatha. This is the first drawing that was made by one of my students that we present in this proposal. It's totally, well, wrong and fake, because there are many things that are not possible. First of all, we have here the chamber of sugar, and we have here the differential vacuum system, and here the jet production target. So as you can see, the beam production target, well, the jet target is overlapping everything. Also, the chamber is overlapping the germaniums, and inside we have a separation of 2 meters between the differential vacuum system and the jet chamber. So we need to work on all these problems and try to match the pumping system on the floor, at least with a good separation, and match the better well the chamber, and include a pipe to separate the chamber from the differential vacuum system. So we start to work. We probably don't have a lot of personnel, but we have a lot of students, which is good. And they help us to mount this. We separate the jet by this pipe, and we simulate the situation to include a 2 meters pipe in between the chamber and the differential vacuum system. And we put a lot of vacuum measurers. So in that sense, well, the test was very successful. We find exactly the same numbers, or practically the same numbers that we have at the beginning, 1.5 times 10 to minus 1 in the case of the jet chamber, which is the nominal value to work. And then at the end, we find 4.1 times 10 to 6 store in the third differential vacuum system, which is a very good pressure to connect to the accelerator. So from this side, we start to be happy, and then we start to work in the design of many planes to correct all the things that we have to build as new to modify sugar. So first, we made an sphere chamber. We separate the jet vacuum system, and well, you can see here the pipe, and you can see here the germanium detectors of Agatha, and where is localized the differential vacuum system, and how it's totally different to the first or initial design that we have at the beginning. This is the most recent mechanical design, where I have to mention that we have a strong communication with the people in Legnaro and Milan, that are the people in charge of these mechanical designs. So, and Carlos Valencia, which is our technician here in Mexico, he's been doing excellent work. And we have now this new chamber that is more similar to a bullet, where we have more space to put our silicon array detectors in this zone, in this region, and we have a good manipulation. We need just this spherical shape in the zone close to the germaniums, and now we have practically this design finished. At the same time, we start to work with some programs to make some simulation about the flux, because we have to modify many things in the geometry. So some of my students, David Godos and Jose Juan Gomez, start to play with these ANSYS that, fortunately, is free for the university, at least some versions, and they start to work to try to simulate, and at least they found these supersonic velocities with the same conditions, so we know that more or less we are in this very minimalistic drawing in the Go way. But then later, what very nice simulation that was developed by Erika Ruiz Martinez as part of the social service, with all the knowledge that has my friend and colleague Libertad Barron. They produced this very nice simulation that you can see how looks the gas inside of some kind of chamber. It's also a cylinder, and you can see this thumb shape that usual of this kind of jet targets. So this work is still in progress. Finally, regarding sugar, let me show this last study, which is related to the turbulence that we produce inside. We make this test to try to see if they affect considerable to the silicon detectors, particularly when they are very thin. So we use this silicon strip detector of 60 microns, but also very thin surface barrier detectors that are here of 7 microns. So we took for hours, a good number of hours, this spectra, and you can see different colors here are spectra taken by every 2 hours. So we could not see any difference here inside and also here. And between them, there are not practically notorious difference in the resolution, which, as you know, could be a big problem when you have silicon strip detectors deteriorating by the beam of current or whatever. So this is the case of delta E, which is exactly in the same condition, and one strip against the other strip. The resolution is big because it's a big peak of alpha that it's a source, probably homemade, that we have here. So the alpha calibration was okay. This is the setup for in these two situations, and is the bachelor thesis of Montserrat Fabiola Silva. And well, this is the conclusion, not any effect observed. So let me finish with this last case that I'm working now in Madrid. It's a nice project to make a recoil separator for ISOs facility, and it's part of these plans of resilience that are promoted by the European Union. Okay. That I directly with financial support from the European Union, but in this case to Spain, and is related to the construction of this recoil separator. So there are strong participation of around 72 members. Also, you can see here Mexico, but leading by Spain, practically, UK, part of France, of course, Switzerland, because it's related to CERN. And we start to work, we start to prepare a proposal 2 years ago, and we have the first grant the last year. No, this year. No, the last year. Well, what are the physics opportunities? Well, to try to measure around 0 degrees from the reactions coming from the chamber that is related to the scattering chamber with exotic nuclei. Different processes, different elastic reaction, column dissociation, transfer reaction, inverse kinematics, multinucleon transfer reaction, fusion evaporation, inverse kinematics, transfer, breakup, fusion reaction, which is currently what we usually measure there, resonant elastic scattering, and so on. This is the main opportunities that we will reach with this new facility. And well, this is the first plane. The first project that we got, this was of €3 million. To use in 2.5 years, I think, and then we are hurrying. So it is funds coming directly to Spain to the University of Huelva and CSIC in Madrid, and the idea is to make the first design, which is a quarter of the biggest one, and is more or less this, that is very small, as you can see. This is the SEC chamber there at Isolde. And this is more or less the plan, to have some quadrupoles, the dipole and second quadrupole, and some beam profile monitors, and finally the focal plane detector. I was working, well, of course, by my experience in this focal plane detector, in the case of silicon detectors, but also these guys that are silicon carbides that are now start to be very big mention in nuclear physics. So I was working in Catania in this system that is for phase system or for new, we can say, exotic beams that we are expecting there. So I used part of this work to start to work as part of this new project with the help of Chiara Guazzelli, my friend and colleague from Milan, and Nara Singh from the University of the West of Scotland. And well, this is the plan in the case of photons that I'm not touching there. I'm touching more the part of the silicon carbide. These are the first prototypes that we have there of silicon carbide, which are, we made 3 weeks ago, this first characterization. We received this detector a month ago, more or less at the end of May. So we have received a 5 millimeters and 1 millimeter detector that we mount in a chamber to start to try with alpha source. We have gadolinium source and triple alpha source. And we found acceptable numbers for these detectors. We use conventional electronics. And in the case of the spectra, we're taking with a digitizer, but from Mesitech. So let me summarize this talk, just saying that the good performance of our detection array, CMAS, is permitting to visit some weakly bound nuclei to get better and precise measurements, and working again in this very nice facility that is Notre Dame, with now the facility that they have, that is Trisol. We started this collaboration in 2019, and well, in 2023, we continue working. And well, in the case of sugar, ADLNL is a project in good progress. We start to work in 2021-22. We continue to work on it, and we are very, very well advanced. And finally, the ISRS project, which is starting, and we have to work on the prototype and the first measurement of the characterization of the silicon carbide detectors were tested, well, as you see, 3 weeks ago. And well, we expect to have the construction of a test bench and to test the many other elements, optical elements, particularly during the rest of 2024 and 2025. So thank you very much for your attention. Well, there are different ways. You can use in some way try to use the Rutherford backscattering, measuring a big time with air per days, and then the spectrum can give you a very well approximation of this thickness. Yes. Your facts here.
Thank you. Well, regarding your gas target in the linear version, you have a very long pipe. So yep. What happens to the beam to cross all this long range in not so good vacuum?
It's something that we thought, and then the idea that we have to try to do this, because we need and we start to speak. It's obviously it's a very long distance that we have here, and the main idea is just try to face to put some kind of quadrupole at the very beginning, and well, this position is not possible to make anything. Fortunately, as far as I understood, if it's not this pipe, is this the pipe is exactly in the same conditions with sugar and without sugar. So as far as I understood, that I very well control the optics to pass there. But of course, you need practically mandatory to put a quadrupole here. it's more or less the idea that yeah, we discuss about that, of course. And we have to. Thank you very much.
How's that? Better. Okay, thank you very much. And thanks to the organizers for inviting me to speak here this week. It's been my first time in Latin America, and it's been wonderful being here. And the rain is making me feel right at home. So yeah, I'll be talking about studying nuclear decays and reactions with storage rings. So I'll give a brief general motivation for why we would like to do this, and then I want to highlight 2 experiments that we've conducted at GSI with the ESR over the past few years, and then take a forward-looking view to a project we have at Triumf called a Tricer storage ring, which we hope to investigate direct neutron capture measurements with. And then we'll give a brief outlook at the end. So this is largely motivated by a desire to understand nucleosynthesis beyond iron. We know that in quiescent burning in stars, we can get up to iron, but then beyond that, everything largely produced by neutron capture reactions via either the S process, R process, or I process, the slow, rapid, and intermediate neutron capture processes. We know about 50% of everything beyond iron is produced in the slow process. So with low neutron densities, we have neutron capture rates on a similar time scale to their beta decay or slower than the beta decay. And so it processes it moves close to stability, typically 1 mass unit away from stability. And then we have the R process accounting for the other 50% occurring in scenarios with much higher neutron densities. So we're getting a lot of neutron captures. We're moving really far from stability. And the capture timescales are much shorter than the beta decay half-lives of the isotopes involved. And then we also have the I process, which is the intermediate process. And as its name suggests, it's intermediate to both the slow and rapid processes, both in terms of the neutron density, the timescale of neutron captures, and the path that it takes. And so it kind of takes this intermediate path somewhere between stability and this really neutron-rich terrain where the R process explores. The key parameter or the key nuclear data that we need for these to understand these processes include N-gamma cross-sections, the half-life of the isotopes involved. For the R process, we're interested in measuring masses, half-lives, and beta delay neutron emission probabilities. And then for the heavier elements involved, the heavier isotopes, also fission probabilities. And for the I process, again, it's neutron capture cross-sections and the half-lives. My work over the last few years has largely focused on these masses, half-lives, and neutron emission probabilities. But as I mentioned, at Triumph, we have this storage ring planned where we'd really love to measure neutron N-gamma cross-sections. I think this is an area that's still very underexplored. On the neutron deficient side of the chart, we have a variety of processes that take place that produce these neutron deficient isotopes. And these typically take place in explosive scenarios. We have processes like, the RP process, the rapid capture process, which is a network of proton captures and the gamma process, which is a network of photodissociation reactions. And most of these, understanding the nucleosynthesis networks that these processes lead to, they rely largely on theory. There's not a lot of experimental data in these areas, and so we're relying largely on theory. And so the goal ultimately is to improve these models by measuring the cross-sections required and measuring the nuclear data that we need to then further constrain these models and improve them going forward. So why would we like to use storage rings? For those who aren't maybe familiar with storage rings, we'll just give a brief overview. As the name suggests, they are rings that store ions in them. Typically made up of drift sections, dipoles for bending around corners, quadrupoles and sometimes hexapoles for focusing the beam, coolers, we can include targets, non-destructive detection techniques so that you can maintain the beam within the ring. And of course, to maintain a beam, we need ultra-high or typically or sometimes extremely high vacuum conditions. And we can then store ions for hours or up to days. And inside the ring, we can separate species by their energy and their mass-to-charge ratio. So essentially, we have a recirculating, recycling recoil separator. And our interest in using them is that in traditional experiments that might use single-pass techniques, we destroy the beam in the process of measuring it. And so if we're looking for some kind of reaction event or some kind of decay, and you implant it into some, say, a silicon detector to then measure the decay, you destroy the beam in the process. And so for every ion, you can only do one measurement. And so for ions that have very low yields, this then you are limited by the yield of your isotopes, and it can make measurements very difficult. At storage rings, we can circulate the ions in the ring at megahertz frequencies. And if we can employ non-destructive techniques, we can then do millions of measurements a second. And so we can increase luminosity in terms of if we have, say, gas targets, thin gas targets in the ring, we can increase the luminosity of the ions exposed to those target ions. And it's also a very efficient use of then low yield isotopes. We can do millions of measurements without destroying the beam, and we can get really high precision measurements. And so in these rings, we can accumulate and recycle the beam. We can decelerate the stored ions, and so we can inject at a given energy and then either decelerate or accelerate them to energies that we're specifically interested in. We can have thin gas targets, which allow the beam to continue recirculating. We can cool the beam, so we want to maintain the smallest energy distribution we can. We want a really monoenergetic beam as best we can achieve. And this allows us then clean preparation of beam and target ions for really low background environments and high resolution measurements. And there's not many storage rings around the world. This is a small, brief overview of what rings are currently available either in operation or under construction in green, or rings that are planned for the future. And so I did promise we would look at some rare decays measured in storage rings. And so the first experiment I would like to highlight is one that we did in 2020, right, the COVID outbreak, to look at the bound state beta decay of thallium-205. And so meteorites preserve isotopic ratios at the time the solar system was formed. We have a lot of the interstellar medium, or the kind of like the pre-solar system gas condensing to form the solar system. And those elemental and isotopic ratios are then kind of, as meteorites form, they trap the isotopes in there, and they preserve those isotopic ratios. And there's been some short-lived, what's called short-lived radionuclides identified. These are short-lived on the timescale of the solar system, so typically have half-lives of 1 million to 100 million years. And as they decay trapped in these meteorites, they form mass fractions in their excess mass fractions in their daughter products. And so they slowly decay over the life of the solar system and then lead to these mass fractions, which we can then measure. And these can be used as cosmochronometers and probes for the conditions at the time, the dawn of the solar system. And 19 of these short-lived radionuclides have been identified all the way from beryllium-7 up to curium-247. And of these, 4 of them are predominantly produced by the S process, but only one, lead-205, is unique in that it's an S-only isotope. So it's only produced by the S process. It's shielded here from any R process contributions by the stable thallium-205. So lead-204 and 205 are both S-only isotopes, and they're useful probes of the S process termination and this thallium-204 branching point and the conditions available in the S process at the time that it reaches this point. If there's more neutrons, you can then proceed to thallium-205, but if there's fewer neutrons, you are going to decay to this lead-204 here. And so it's a useful probe of these conditions. There is a problem, though. For lead-205 to be a useful probe, it has to survive until the solar system forms. And in the 70s, there was a problem identified with this 2.3 keV half-minus excited state, because this can be very, very easily populated thermally. And the half-life, of lead-205 is 17 million years, and it decays via electron capture. But with this half-minus state, there was concern that the reduced spin difference between the excited state and the thallium-205 ground state would dramatically reduce the half-life of this decay. And all of the lead-205 would be destroyed before it even entered the solar system. And so it would no longer be a useful probe or useful as a cosmochronometer. However, bound state beta decay comes to the rescue. So bound state beta decay is a unique type of beta decay. Usually something beta decays, its electron shells are filled, and so the electron is emitted into the continuum. Bound state beta decay can occur in highly charged ions, either typically fully stripped or in a hydrogen-like state. And in this case, you can emit the electron directly into this K-shell, this low-lying K-shell orbital. And so in doing so, you kind of regain the binding energy of the electron. And this, in the case of thallium-205, has the impact of, in gaining this 85 keV from the binding energy of the electron, the Q value of the lead-205 electron capture was only 50 keV. And so you now have enough energy for the fully stripped thallium to decay into the lead-205, and you can reverse the flow of this decay. There's huge variations in the predicted half-lives of this reaction, but it could be a possible solution to this problem of all of the lead-205 being destroyed before it entered the solar system. And some colleagues performed some simulations here to look at the predicted decay rates of both the lead-205 electron capture and the thallium-205 bound state beta decay. And you can see as you kind of pass this 100 million Kelvin threshold, the bound state beta decay actually becomes preferential. So to study this decay, we then have to be able to store thallium-205 in its fully ionized or hydrogen-like state, which is not trivial. And so this is where we then went to the ESR. We desired to produce the thallium-205, separate it in the FRS and inject it into the SR, and then store it for a range of times so that we could then, at the end of a given storage time, look at the ratio between the thallium-205 and the lead-205 to then try extract a decay rate. And with a half-life of a predicted half-life in the hundreds of days region, it's a non-trivial thing to store this for several hours at a time. And because of the high charge state, you can have instant recombination with any residual gas left in the ring. And so we needed very high vacuum conditions. That experiment was predicted, or that experiment was first proposed about 30 years ago by Fritz Bosch, after this problem was identified initially in the 70s. And so 30 years later, in 2020, we conducted this experiment. We did 10 storage times for the thallium. And then upon their extraction, or at the end of the storage time, like I say, we then measured the ratio between the thallium-205 and the lead-205 to extract a decay constant. And determined, this was the PhD work of Guy Leckenby at Triumf, along with Rangadeep Singh and Ruju Chen at GSI. And so after 30 years after this was initially proposed, we have measured a half-life of 291 days, very different from many of the predictions. They were going down to 60 days, up to hundreds and hundreds of days. And we have recently submitted this to Nature. This is under review with Nature. And this led to a log FT value of 5.91. Again, very different from what was previously predicted by the theory experiments. So it really emphasizes the importance of doing this measurement and actually constraining this half-life. And we have several other papers in preparation looking at the astrophysical impact of this newly measured half-life. I would also like to look at an experiment we did looking at proton capture reactions in the ESR. So, like I said, we can include a gas jet in a storage ring. It's a thin gas target, so you don't degrade the beam too much. And then we hope to observe proton captures in this hydrogen gas target. And then because the ring separates things by their mass to charge, after passing through this first dipole, anything that captures a proton will have a lower mass to charge ratio, so it would bend more to the inside of the ring. And for instance, if there was an electron capture, its mass to charge ratio will be increased, and so it will move more towards the outside of the ring. And so Jan Glorious at GSI has developed this proton capture program using these in-beam detectors to look at the products of these proton capture reactions. These are then normalized to some very well-known atomic processes, and so you get electron recombination in the gas, and there's germanium detectors surrounding the gas target, and so we can then normalize these proton capture reactions to these very, very well-known atomic processes that we can measure in the gas target. This was started a few years ago with 2 stable beam measurements. Initially with the proton capture on ruthenium-96. It was a successful pilot experiment. This was done with some detectors that were in what we call a pocket, and so they were behind atmosphere, but injected into the ring, but behind a thin stainless steel window. And so we couldn't access the gamma window because the energies of the isotopes were too low to penetrate the stainless steel window. But we did do 3 measurements of this ruthenium-96 proton capture. And so you can see already we can start to then distinguish models from one another and start to constrain some of these models. This was then followed up by proton capture on xenon-124. This was then using a vacuum-compatible system. So there's this silicon detector that's installed inside the ring and allows us to push to much lower energies. And so they did 2 measurements inside the gamma window of this reaction. And this shows us that we can obtain local agreement with data by tuning nuclear inputs and pin down some key reactions. But really, for a global improvement of theory, we need constraints at lower energies. These models are widely different, and you can see that the work of this xenon-124 proton capture can dramatically constrain these models. And we need to do this on exotic nuclei. So this is where we come to then the first radioactive P-gamma measurement with tellurium-118. And so there was 2 measurements done with this. The first measurement was at 7 MeV per U with 40 hours of data taking, and we can see a clear proton capture signal here. This is Rutherford backscattering from the stored ions in the target. And then we see this clear evidence of this, the proton capture product here. And this we obtained about 300 counts for about 7.5 counts an hour. The second measurement was done at 6 MeV. We had fewer ions for this measurement, and a weaker signature, and so required longer data taking, but you can still see this, this proton capture product standing out from the background here. And this is the analysis. This is the PhD work of Sophia Delman, a PhD student at the University of Frankfurt, which is now complete. I think there's a publication in preparation. But from these measurements, she was able to obtain cross-sections for these reactions. So again, this hasn't quite got into the Gamow window, which I've indicated here, but we are already seeing a push down towards the Gamow window and a differentiation between the models. And this was the first direct measurement of a proton capture reaction on stored radioactive ions in an energy range relevant for nuclear astrophysics. And so Jan Glorious and Yuri Litvinov are really pushing this program and spearheading this program. And the goal is to expand this to more key nuclei of interest for these neutron deficient reaction networks and address key reactions of explosive nucleosynthesis. So I come back to this slide from the start, and I highlighted earlier that N-gamma cross-sections, the neutron deficient side of the chart has fewer isotopes in than the neutron-rich side of the chart, and so we would love to explore this more, and a big thing that we're lacking is N-gamma cross-sections. These are not trivial to measure. Especially if you want to do it on radioactive nuclei. We have a problem because radioactive nuclei obviously decay, and so we can't always build a macroscopic target. We can't make a macroscopic target of something if its half-life is too short. Some isotopes, this has been done in the past when they have very long target half-lives, but if you're working with a short-lived target, that won't work. You also can't make a neutron target because they also have a half-life of 10 minutes. We can move to surrogate reactions to use, well, these surrogate reactions to investigate direct neutron capture reactions. But this requires a theory component, and the theory isn't always precise. And if we look at the current status of this, we can see there's a lot of work to be done. And so with this highlighted here, some stable isotopes where there aren't measurements of any neutron capture cross-sections, but in green, there are quite a lot of stable isotopes where direct neutron capture measurements have been done. This is quite straightforward. You can build a stable target, you can irradiate it with neutrons, and you can measure the cross-section. But then if we move to radioactive isotopes, you can see there's only a handful of these orange squares where they've been measured with direct measurements, and these are the ones where they have long enough half-lives that you can build a macroscopic target and you can irradiate it with the neutrons. But then there's only a handful more of these yellow and blue squares where surrogate methods or something like the Beach-Roswell method have been used to do neutron capture cross-section measurements on shorter-lived isotopes. This is really important work. If you look to the theory predictions, some of these models, like non-smoker, they have variations of factors of 2 to 4 around stability, or something like TALIS, there's variations of over factors of 100. And this is done by varying the level densities and the gamma strength functions. But with such large variations in these predicted capture rates, having experimentally measured direct neutron capture data is really key in pinning some of these down and improving these calculations. So there's a lot to be done in the coming decades, and we would love to measure more direct neutron capture cross-sections of short-lived nuclei in energy ranges that are useful for nuclear astrophysics, so keV to a few MeV. And then here's where the Triumph storage ring comes in. And so the idea here is to install a storage ring at Triumph and then couple it to a neutron generator that will produce neutrons real-time, a high flux of neutrons, and we can pass the storage ring through this field of neutrons and hopefully measure neutron capture reactions there. And again, with it being a storage ring, you have this benefit of recirculating the ions. You then get an increased luminosity from the multiple passes through your neutron field. And this combination of the storage ring and the neutron generator is what we're calling the TRISA, the Triumph storage ring. And if we look back to this slide with the storage rings, and then highlight the ones where they are proposed to include a neutron target. There's even fewer. So there's Derica in Russia, and then there's a Triumph storage ring, a Triumph, and then Los Alamos are also proposing a ring at their facility as well. There's other ideas complementing this, and so it's been proposed to install a storage ring at a nuclear reactor, and pass the storage ring through the reactor core to access the high flux of neutrons there. This obviously has its drawbacks. I think trying to convince someone to allow you to put a beam pipe through their reactor core is going to be a tough sell for most, but it has been proposed. And then there's also this project at Los Alamos to couple a storage ring to a spallation-based neutron target. And so using their proton driver to generate neutrons and again, pass the storage ring through that. At Triumph, we have space in the ISAC-1 hole where we are projecting that we would like to install this storage ring. And the focus would be, and so we can leverage the benefits of Triumph. We have an existing ISOL facility, we can install the storage ring, and then these neutron generators are actually quite compact devices. And then we also have the benefit of aerial coming online in the near future. And so the focus would be on neutron capture cross-sections of heavy nuclei with masses typically greater than 50, at astrophysical energies from 100 keV to 2 MeV. So it'd be a low energy storage ring, so we can access these astrophysically relevant energies. And we would be able to store stable ions and radioactive ions down to half-lives of seconds. And so we're somewhat limited in that you have to extract the ions from the target, the ISOL target, move them through the facility into the storage ring. You then have to cool them. That typically can take seconds, and then store them stably in the ring. And so there is a lower limit on kind of the half-lives of these isotopes that are imposed that we can do this measurement with. But we would couple the ring to this compact neutron target. We're in contact with a company in America that produces these. And we are using the specs of their devices to then optimize and design moderators. These are DT generators, so producing 14 MeV neutrons. So we need to moderate the neutrons down to thermal energies. And so we're working on the design of this moderation, trying to maximize the flux of the neutron field in this reaction area. Sorry. And the goal is to aim to achieve a neutron flux of 10 to the 8 neutrons per second per centimeter squared. Reaction products would then be extracted by a Wien filter and detected in a recoil separator in the center of the ring. This is under active design. This is still in the very early stages of this process. And so we are really encouraging any community engagement. If you have an idea of something that you'd like to see, we're thinking of including a gas target. That's from other colleagues that we've spoken to is a must-have. But if there's anything else that you'd like to see or anything that you think would be achievable a ring like this, we would love to hear. And this is really being pushed for by Iris Stillman. And there's a paper from last year where she looked at this ring. So we are, like I said, we're limited. There's a minimum half-life imposed, but we also have done some kind of calculations to look at what kind of event rates we can get from these reactions. So the reach depends on the neutron densities, which is why we're trying to maximize this neutron field as much as we possibly can. And then there's some facility-dependent parameters. So the beam lifetime inside the ring, that depends on the energy of the products. The lower energy of your stored ions, the more likely they are, or the quicker the quality of the beam degrades and you lose your storage. And then the vacuum conditions in the ring. So we want to achieve the lowest possible vacuum we can to avoid any interactions with residual gas molecules in the ring. The injected beam intensity, of course, we want to maximize that. But then the beam energy also has an impact in that the higher energy you have, the higher your rotation frequency or your orbiting frequency. And so this all leads to two kind of example cases that we've looked at with a cross-section for interaction of 100 millibarns or 1,000 millibarns, and then orbiting frequencies of, say, 135 kilohertz or 500 kilohertz, leading to anywhere between 1 event per day up to about 40, 50 events per day. And so this is the kind of numbers that we're looking at here. This, of course, is not a short-term project. We have already started with the design work for some of these neutron moderators, trying to maximize the neutron field there. And later this year, are submitting a grant to do a feasibility study with these neutron generators to see really what kind of fields we can achieve. But this is ultimately, we're kind of looking for mid-2030s for the first commissioning experiments of this facility. It's a big collaboration. There's many people involved at Triumph from the Physical Sciences Division and the Accelerator Division. And we have colleagues also at the University of Victoria and McMaster. But then we're also in frequent contact with our colleagues at GSI because they have a wealth of storage ring expertise there. And so again, Jan Glorious and Yuri Litvinov. And then our colleagues at Valencia, who have been really instrumental in designing these neutron moderators and doing the work there. And also colleagues at Los Alamos. Oops. So in summary, I think storage rings provide us unique capabilities, complementing and sometimes improving upon traditional single pass techniques. They allow a really efficient use of low yield isotopes for high precision measurements. And a wide range of nuclear properties are accessible for measurement in these rings. And then looking forward to the future, our Triumph storage ring project would be a unique and pioneering facility, offering exciting access to direct neutron capture cross-sections of radioactive ion beams, which currently is not available anywhere else. And thank you very much.
Please, time for questions. Yes, please.
Very nice results. I have two quick questions, probably. One is there any existing ring of similar energies as the TRICE?
The Cry ring would be the closest. And so this, the synergy grant that I mentioned, the plan or the hope is to purchase some of these neutron generators and then install them at the Cry ring at GSI. And so it's a pre-existing ring. We can do some confirm our optimization of the moderators. We can investigate, is this actually a feasible technique at the Cry ring before we then commit to doing this at Triumph.
Okay. And the second, the cases you showed for estimated events per day were for 10-second isotopes.
Mm-hmm.
So if you want to go to kind of our process, I mean, the more our process in the more neutron-rich scenarios, you have half-lives below seconds. So do you think how far from stability is that you would like your design to go? And can you reach our process?
No. This is really looking at kind of like I-process nuclei. I think the limit, when we've been discussing this at GSI for the ESR, kind of you're looking at a few seconds before you can do a measurement. And so it takes a few seconds to inject the isotopes, cool them with either the electron cooler or the stochastic cooling. And that's the order of a few seconds. And so I think really that's currently the lower limit that we could aim to achieve here.
Okay, thanks.
So you already answered my first question, which was just this last question, which was asked. Very nice technique. I just wonder what are the detection efficiencies, because I don't see any efficiency here. You're assuming that the cross-section is measured with 100% here.
Sorry,
The efficiency of detection, right? Because you have to detect
yes.
the outgoing particles. And from our experience at the ESR, of course, we always have this phase space problem, right? And we cannot put detectors everywhere.
Mm-hmm. So this is something that is very much still under consideration. Okay. The idea, because with, yes, the idea being to install this Wien filter and the recall separator in the ring. But no, this is, we've been working with okay. Barry Davids and the accelerator group at Triumf to kind of have a more concrete idea of what we could aim to achieve with such a filter and recall separator combination, but we don't have anything concrete.
Okay,
yet.
but so that number has to be put in there, which may actually result in much lower count rates. Thank you.
More questions? So you use gas target and only gas target, right? Two different gas targets. One is for jet gas and the other one is
for the Triumph storage ring, or no? It would just be a gas jet tank.
just a gas.
Yeah, just one. Yeah.
Thank you. Okay, let's thank you. Our next speaker is Armando. Marcilei. Marcilei. Thank you. So, thank you very much.
Okay. Hello, everybody. And I would like to thank the organizing committee for inviting me to talk about endurance of HOPG to ionize radiation, advancements in target development for nuclear reaction. Okay, I probably with the pointer. Okay. And the motivation for this research is the NUMEN project, Nuclear Matrix Elements in Eternaless Double Beta Decay. And the Professor Oliveira told some details about this reaction yesterday, but it's in this project, the nuclear double charge exchange reactions are investigated at Laboratorio Nazionale del Sul in Catania, Italy. And these reactions presents low cross sections, so are produced by heavy ions with high intensity, generating large amount of heat in the target that must be dissipated. Here is the key point, because you need substrate for the target that must have excellent thermal conductivity. In this project, the ion beams will have up to 60 MeV per nucleon and intensity up to 30 microampere. For this, the accelerator is being updated. And regarding the target that's subjectively developed in this research, several targets in nuclear reaction are metallic elements with a low melting point. And HOPG, the high-oriented pyrolytic graphite, is a great candidate to be used as substrate or packing for the target, because this material presents very nice properties. For example, high thermal conductivity. But the vacancies produced during radiation decrease the thermal conductivity. Okay, so you have a complex problem. You need different scientific knowledge to have ideas to solve this problem. So use it in this research. Applied nuclear physics, solid state physics, material science, and develop new instrumentation. So now we are studying about radiation factors and ionizing radiation effects in the target, particularly in HOPG, through simulations of the interaction of different beam and targets to perform experiments that simulate the damage to HOPG generated in nuclear reactions. But what is HOPG? HOPG consists of carbon atoms arranged in hexagonal structure, belongs to lamellar materials. Summarizing, this material is composed of graphene foils, one top of the other. In blue and red, you can note. In black is the normal vector perpendicular for each graphene foils, okay? It's important to show the hexagonal structure because the physical properties of HOPG are characteristic of the crystal lattice structure and present different results when measuring in basal plane and perpendicular to basal plane. Here, the atoms carbon are placed in B and AB position, and here the C, the perpendicular to basal plane. In basal plane, for example, the HOPG considered in this study is 2 micrometer thick with 1.7 kilowatts per meter Kelvin, 3 times larger than copper, for example. Okay, but the ideal HOPG presents normal vectors completely parallel. What experimentally it's impossible. So the delta angle defines the quality of this material. This angle between 2 consecutive normal vectors. In this research, we use about 0.4, 0.8 degree. That defines very good quality for this material. Okay, now you need to understand about the correlation between damage in this target or backing of the target and the physical properties, specifically thermal conductivity. One of the most important techniques to verify about this is Raman spectroscopy. Here I show the spectrum, Raman spectrum for HOPG. G-band is related with the crystalline structure of HOPG, and D-band is related with the damage in crystalline structure. So the ratio between D and G intensities defines the degradation in this material. And the other important characterizations, X-ray diffraction can indicate changes in the crystal lattice, change the position of the diffraction peaks, the width and intensity of these peaks. Here, I show the diffraction peak obtained in this research for the HOPG used in this study, okay? With high degree of purity and high degree of ordering of atoms. And what is the relation with the thermal conductivity? Oh, thermal conductivity depends on the temperature. It depends on the allotropic forms of carbon. Okay, this diagram based on average values reported in literature shows that in room temperature, for example, the pyrolytic graphite, there is HOPG, in basal plane, presents thermal conductivity about 1.5 kilowatts per meter Kelvin. While for amorphous carbon, this value is 1.5 watts per meter Kelvin, so 1,000 times smaller. According to the literature, a minimal structural damage in graphene causes abrupt decreases in thermal conductivity. So we hope that for HOPG, this behavior is the same. Okay, all only 0.25% in vacancies concentration decrease thermal conductivity in about 50%. So you did several simulations for different nuclear reactions proposed by NUMEN project. Using transport for ions in matter, it's very well-known program created by Ziegler and Biersack. And here I will show some results by NEO 20 with 270 MeV into natural thin evaporate over HOPG, where in this graph, we note the total vacancies as a function of radiation timing for 3 different flux. So it was possible to determine the ratio between total displacement for total HOPG atoms. So when this value is equal 1, the HOPG has become amorphous carbon. And for this flux, for example, in 500 hours, this happens. Okay, consider these simulations. In 3.5 hours, the HOPG present about 0.25% vacancies concentration, decreasing thermal conductivity in about 50%. Now, you need to prove experimentally about this correlation between damage in crystallets and degradation in thermal conductivity to determine the lifetime of this material as a heat sink to use it to dissipate the heat. Okay. The first experiment was using neutrons. Why neutrons? Neutrons cause damage in crystalline lattice, so it's possible to verify the interaction between beam and the HOPG and nuclear reaction generating neutrons too. Okay, remember that damage is not caused directly by neutron in the target, but by the product of the neutron reaction in HOPG, that are ions. We use a generator where neutrons are produced by deuterium tritium. Deuterium plus tritium produce helium plus neutron with 14 MeV. We exposed the HOPG to 14 MeV, and we characterize these samples using X-ray diffraction, Raman spectroscopy, atomic force microscopy, scan electron microscopy, and we measure the thermal conductivity, electrical resistivity, and magnetic resistance. Here, I showed the setup used in this experiment. Here, you observe the neutron generator and the HOPG samples are placed on the table. I show the important results obtained by flux simulations in the other work of the neutron flux in magnetics experimental hall expected in NUMEN experiment. Magnetics is a magnetic dipole that deflects the ion in the experimental hall. These results were based in the neon 20 beam interaction with germanium 76 targeted with carbon backing, so HOPG. Look, in this region where the target is placed, we expected about 10 to the 16th neutron per square centimeter per second, where about 10 to the 15 are fast neutrons, and we are using the fast neutrons, 14 MeV. So we are in this region, okay? This is the neutron energy spectrum obtained for this flux calculation. So we are representing a portion of neutrons produced in Newman experiment. Now about our experiment. We use a silicon detector to monitor the reaction. Here I show the particle spectrum where it's possible to note the alpha and proton peaks resulting of the reaction of neutron plus silicon-28. So you can consider that byproducts were generated resulting from the interaction of neutrons also with carbon nuclei. We verify the products of neutron reactions in carbon using this program, PACE4. There is a fusion evaporative program. So carbon-12 and beryllium-9 present a higher cross-section correlated with neutron channel and alpha channel. And we consider these ions as to verify the damage generated in HOPG. Here, I show the results by Triumf simulations. The total vacancies generated by carbon is about 500 vacancies per ion. The Bragg peak is here into HOPG. And the beryllium-9 generate about 50 vacancies per ion because pass through the sample. And now, this table considers the experimental methodology correlated with the results obtained with simulations. We exposed the HOPG samples to different exposure time here with this fluency, neutrons per square centimeter, generate about 10 to the 17th, 10 to the 18 vacancies per square centimeter. Consider the results in FLUCA simulations expected in experimental hall at Newman experiments. This study is equivalent to 27 hours of exposure to fast neutrons generated in the Newman experiment. Okay, now about the characterization of this backing. We use it to know about the microstructure characteristics, the AFM and scanner electron microscopy. The characterization about orientation and disorder in HOPG crystallography. We use the Raman spectroscopy in X-ray diffraction. And finally, the effects of the loss of crystalline structure on the physical properties were observed. So thermal conductivity, electroresistive, and magnetoresistance. Now, here, we got a lot of results and images for each sample, but here I show only representative images of each sample. Using scanner electron microscopy, it's possible to note the degradation of this material with irradiation. The graphene foils appear in great number, as if they were built up, an effect of lamellar structure. This indicates that the bonds between graphene layers are weaker. So the HOPG quality decreases. Now, using atomic force microscopy, it's possible to verify different graphene layers. Here in square region, 3 layers. It's possible to note in zoom, where we measure the step between layers and roughness in each layer. For example, between these 2 layers, the step is about 1.50 57 nanometers, while in this case, between this, 0.63 nanometers. Now, I show you the comparison of the pristine sample with the sample after first irradiation. It's possible to note the different surface, and surface appear with different number of layers and imperfections, some imperfections. Okay, we measure the step through the profiles. We verify several profiles in each sample. Here, you note the different height and different width for the steps. So we consider the average for each parameter that we measure. And now the roughness in this region. For example, the roughness here in NA region is about 0.32 nanometers, while in this region is higher, 0.8 nanometers, because of this imperfection in this region. And here I show the image obtained for pristine and the image for after the last irradiation is totally different. Summarize, and the step between layers increase from 0.9 nanometers to 1.3 nanometers, and the roughness is practically the same. In according what we observed with scanning electron microscopy. Now, about the crystalline structure. Remember that I told you that the intensity, the width, and the position of the diffraction peak indicates the degradation in crystalline light. I show exactly this. And we use a transmission mode to perform this measuring because this presents a very nice resolution. Here, it's very small, the width for this peak, okay? And about the LEDS parameter, in basal plane, perpendicular to basal plane, the variation in crystal LEDS parameters is small, and the change in the width is up to 8%. Okay, about the Raman spectroscopy. An average of 15 Raman mapping were performed in different points in each sample, considering the two surfaces, front and back. It's very hard characterization. Again, we have a lot of images and histogram to present, but I will show only one representative for each sample. The histogram represents the distributions of the intensity ratios of the D per G bands in analyzed area. Remember that the G is correlated with the degradation in crystalline structure. And here, for pristine sample, the average for D per G, it's about 0.0035. And after 0.042, the after second irradiation, 0.055, and the last, 0.092. It's easier to observe this in this graph. D per G is a function of neutron fluency. This ratio increases with radiation, and here, the D band's intensity is associated with the presence of the defects increase with radiation. Okay, and what is the correlation with physical properties, specifically thermal conductivity? We need to know the lifetime of this material to use in nuclear reactions. Okay, here I show about the electroconductivity, okay? At room temperature aligns with the manufacturers provide value. There is 2.8 million per ohms meter. It's very good result, okay? We determine the residual resistivity ratio that indicate the crystalline quality of the materials. Look, this value decrease with radiation, okay? From 9.8 to about 6.4. And now about magnetoresistance. Magnetoresistance is important in low temperature. At low temperatures, the effective scattering influences the electrical resistivity, thus result in variations in the magnetoresistance relative to crystal perfection. Okay, here about 4 Kelvin, you note that this value decreases in about 45%. Here, the very nice results for thermoconductivity and magnetoresistance. The thermoconductivity as a function of the neutron fluency, and in black, the magnetoresistance. Both decreases about 45%. So there are a strong correlation between this measure. It's very interesting because literature, in literature, the decrease in thermal conductivity is related to the phonon of the lens. But here is related with the electrons mobility in the lens. So you need to investigate about this with more details. But it's okay. It's not important for determine the lifetime to use in nuclear reactions, okay? Summarizing, AFM scan electron microscopy indicates that the bond between graphene layers becoming weaker with the effects of radiation. The Raman showed that disorder increases with radiation. The X-ray diffraction showed the alteration in LED's parameter, indicate alteration in crystalline structure. Magnetoresistance has a strong correlation with the thermoconductivity, indicating that even minor damage to the crystalline structure degrade its physical properties. Okay? The HOPG was 1.7 kilowatts per meter Kelvin in pristine sample. After the last irradiation, this value is 935 watts per meter Kelvin. Even so, after degradation, this thermal conductivity is still higher than that of copper, for example. Okay, but take care because this is only due to fast neutrons. A portion of the radiation that target will be exposed in no-man experiment. Have I been damaged? Remains to be checked. It's very important for the experiment. Okay, we start to study about this. We did the reaction using 35 chlorine with 49 MeV into HOPG in pellet accelerator at Universidade de São Paulo, which simulates the same damage obtained by intensive beams for Newman. Here, I show the results obtained by Triumf simulation for different nuclear reactions, some proposed by Nuclear Project, and it's possible to observe that using chlorine 35, it's possible to reproduce the same damage concentration, create with reactions proposed by Nuclear Project. In this moment, we are analyzing the results, okay? But in August, We will do again the same reaction, considering some improvements. Here, we are building a new instrumentation which allows thermal and electrical measurements during nuclear reaction. We tested it in the last month, and we reproduced the experiment with improvements in August using this equipment. This is a prototype of this equipment, but I will show details about this in the next opportunity. The collaborators with different expertises from different institutions. Thank you very much for this collaboration, and thank you very much for your attention.
So thank you very much for the presentation. I have a question which relates with your first slide. When you mentioned Numen as a way to get information about matrix element for neutrino-less double beta decay.
Yes.
Well, I have a contention about that. Is that the momentum dependence of the transfer that you got in DCX reactions has nothing to do with the momentum dependence of the nuclear matrix element for double beta decay.
Yeah.
So the importance of your experiment is just the information about the nuclear structure, I mean levels and so on of the system which are involved in double beta decay, not to extract matrix element from double beta decay from the DCX cross-section. This is impossible. Thank you.
Okay, this is a comment only. Yes? Okay, thank you. Okay, after the experiment, I cannot and discuss about this in this moment. It's impossible, but we think that it's possible, but I will show. Okay.
Marcilei, after this test of, with neutrons, do you think that this HOPG it's a good material to continue working proof?
Yes, it's very good material, but the problem, as I told you, is that depends of the damage in crystal LEDs. We are very fun about this to see if it's possible to change the target during the experiment. And it's necessary to verify if it's worth, okay? I don't know the answer yet because you need to verify the results for the reaction using 35 chloride. That is the more important than the neutron reaction in this case.
Yes, you mean the charged particle interaction with the target at high energy and high current?
Yeah.
Okay.
So I apologize if this sounds like Osvaldo's question.
No.
But
no problem.
So I said that I just want to continue this line of thought about the motivation of the experiment.
Okay.
So he mentioned the momentum dependence, right? The operators that are going to connect the different states are also very different from what you use in neutrino beta decay. So is the main motivation trying to characterize the initial state and the final state, or what is the main motivation behind Numen?
And what question? The main motivation for this study, you can know exactly this your question.
Yeah, so my question is that the operator that connects the states in neutrinoless double beta decay and in this double charge exchange, they're very different.
Yeah.
So Clearly, it's very hard to say, I'm going to extract the matrix elements of relevance to the neutrinoless double beta decay program. So what I want to understand best is what is the main science motivation? Is the characterization of the structure of the initial and the final state, given that the matrix elements that connect them are very different? I don't know if I explained it myself.
I think that I can't to answer this question with details because it depends on a lot of conditions to answer about this. But I think that we can talk about this because these reactions present low cross-sections. So the results depend of the ion beam, the intensity, then target, then magnetic dipole, because the flux selected the important ion. So depends about a lot of things, okay? Just this. Now the answer for you. Yeah.
So the name Numen at the beginning means nuclear matrix element for double beta decay. That was the Francesco the first initiative. And then we were having some workshops and talking to them. And he wanted to express the cross-section for DCX as a function of matrix element that could relate to double beta decay. But as we said, this is simply not possible. It doesn't mean that the project is not valuable. It's very valuable to illuminate the spectroscopy of the states which are participating in double beta decay. So the claim may be better to say, this is a very good spectroscopic tool to illuminate final states with 2 neutrons less and 2 particles more than the initial state with 2 double beta decay. If you have this information, we are going to be very happy because then we can take these states, check our codes to the energy levels and wave functions of that, and then with that calculate nuclear matrix element for double beta decay.
Yes, the comment again. Thank you, Professor. Thank you. No, yes, thank you. Gamma ray damage? In this case, no, because the most important interaction to cause damage in the HOPG is in crystalline structure. So the impact of the ion beam with the crystalline structure is more important. And the neutrons too, because the neutron directly don't cause damage, but the product of the reaction causes damage in the structure, the crystalline structure. But I think that the ionization in the track, okay, I think that can cause damage too. But we need to verify with detail about this. Okay, thank you.